Example 8.9. Here we have a block having a mass of 0.8. M equals 0.8 kilogram. Is given an initial velocity VA. VA equals to 1.2 m per second. So initially we have the block of mass m is moving to the right with a velocity VA and collides with a spring of negligible mass and with K equals to 15 Newton per meter. Part A assumes that we don't have friction between the object and the plane. So in the part A, let F equals to O. Calculate the maximum compression of the spring after the collision. Okay, let me. Here we have the system. As you see, we have, let's take a system with the state 1. With the state 1, it's before the collision, where the object M is moving to the right, and we have the spring at the equilibrium position, X equals to O. Okay, in this state, we are before collision. Okay, what we have here, the spring has no elastic potential energy, so the potential energy elastic equals to O because X equals to O. Second, it's all about the spring. Now for the object, for the mass M. This mass M has a velocity. So here we have a kinetic energy. Kinetic energy equals to half mv squared. In this case, V equals to VA, okay, square. And as you see here, we have a horizontal motion. We can have the same level. We don't have height. So we don't have a gravitational potential energy here. XY is here. So we don't have potential energy G equals to O. We are talking about the first state. So we have PEE1. We have the kinetic energy of the state 1 and the gravitational potential energy of the state 1. Now I take state 2. In the state 2, I am during the collision. After the collision, the system of the spring and the block is moving to the right. And here we have a compression of the spring. Okay, so the state 2 is during the collision. We can say during collision. During collision, let me see. About the spring, have you a compression? Yes, because the spring is during the compression. We have XB. So here we have elastic potential energy equals to half kx squared. Let's say during the state we have xb here, okay, xb. About the mass m, do you have velocity? Yes, we have velocity. So we have kinetic energy. So here in the state 2, we have kinetic energy equals to half mv square. Here we have Vb, okay, Vb square. About the potential energy, gravitational potential energy, we don't have because we are always on the same level. So we don't have PEG. We are talking for the state 2. In the state 2, here, PEE2, kinetic 2, and PEG2. Let's take the third state. In the state 3, when the system is at the maximum position, at the maximum displacement, and we have here a maximum compression of the spring. So here we have a maximum compression. What do you have here? For the spring, do you have a compression? Yes, we have X maximum. So we have elastic potential energy. Potential energy elastic equals to half Kx maximum square. Do you have velocity? No. At the maximum position, we don't have velocity. So we don't have kinetic energy. So the kinetic energy equals to 0. And also we don't have potential energy G. We don't have H equals to O. Here we are talking about the third case. 3, 3, and 3. As you see here, we have a isolated system. We can use directly delta mechanical energy equals to delta potential plus delta, let's say delta kinetic plus delta potential equals omega F. In the part A, we assume that F equals to O. In this case, we have a conservation of mechanical energy. Okay, so delta mechanical equals to O, and mechanical ME initial equals to ME final. When I say initial and final, I mean at any state. Initial, it can be 1 or 2 or 3 at any position. So here we can say ME1 equals to ME2. We can say ME2 equals to ME3. And we can say ME1 equals to ME3. We can choose any one. It depends our problem. I want to calculate X maximum. So I need to find, to use the second one or the third one, because I need to calculate X maximum. It's during the third state. If I take the second one, 2 and 3, in the second state, we have VB unknown, and we have XB unknown. Okay, we have two unknowns. And in the third case, we have X maximum is unknown. So we get finally one equation with 3 unknowns. So we cannot use the second one. For the third one, between 1 and 3. For this, okay, I have to use this one. In the first one, we don't have any unknown. We have VA, we have M, and for the third one, we have only one unknown, X maximum. So we have to take this relation between 1 and 3. You know the mechanical energy equal to the summation of the kinetic and the potential energy. Here we have kinetic E1 plus potential elastic 1 plus potential G1 equals to kinetic 3 plus potential elastic plus potential G. Okay, we add these values, and here we add these values. Okay, what we have, kinetic equals to m over 2 VA square. We don't have potential here. At the third case, we don't have kinetic. We don't have kinetic. We don't have PEG. We have only have Kx maximum square. We have to calculate it. So we can eliminate 2 and we calculate x maximum equals to integral of x equals to m v a square divided by k. Here we have m equals to 0.8 times VA equals 1.2 divided by K equals 250. We get X maximum equals to 0.15 M. This is X maximum. Okay. Now it's a part A. So let's go back to the part B. Suppose a constant force of kinetic friction. Now we have an interaction between the object and the plane. With mu kinetic, here we have mu kinetic equals to 0.50. If the speed of the block at the moment it collides with the spring is VA equals 1.2. Okay, VA at the moment of collision equals 1.2 m per second. What is the maximum compression XC in the spring? XC maximum, how much? Okay. Here, what do we have? Here we have mu equals 0.15, I think. 0.50, 0.5 mu k. In this case, when the object, listen, when the object moves to the right, just at the moment of collision, VA equals to 1.2 at this point, just before the collision, before the compression, okay? So we can say here, at this moment, here we have VA equals to 1.2. Okay, I don't talk about this. Okay, and I want to find X maximum. Okay, so we can take state 1 and state 3 simply. But here, be careful. We have delta mechanical energy equals to delta kinetic plus delta potential equals omega F. Here we have F. So we don't have a conservation of mechanical energy. No of mechanical energy. We have to use this relation between. So I take the state 1 and the state. We have to precise between which states we are working. One is just before the collision, and the final state, state 3. We can say we have to use this relation. Delta kinetic equals to kinetic final minus kinetic initial plus delta potential. Here, I don't talk here about the gravitational potential energy, because in general, delta potential energy equals to delta potential energy G plus delta potential energy E. Here we don't have height, so we can neglect the PEG. We are talking just about the elastic potential energy. So here we have the final elastic potential energy minus the initial elastic potential energy equals to the work done by F equals to minus F times the displacement dx, of the distance of the between the positions. Okay. Now in the state 1, before in the state 1, what we have? We don't have x equals to O. So we don't have, in the state 1, we don't have elastic potential energy. Okay? Potential energy elastic equals to half kx squared equals to O. And at the state 1, we have a velocity of the object. So we have a kinetic energy. So here we have kinetic energy equals to half mva squared. For the state 3, what do we have? We don't have velocity, so we don't have kinetic. And we have a maximum kx maximum square. It's a new x, okay? New x, not the same as before. Equals to minus F times the displacement. Okay. Now I need to calculate x maximum, x prime. Okay, here we have x prime in this case. We have VA, we have M, we have K. we have to calculate F. You know here F equals to mu times N, mu kinetic times M, dx. dx is the displacement between the initial state and the final state. You see here, the displacement is from here to here. Alors, it's the same value of x prime. It's the same. I'm talking about the displacement between the initial state and the final state. I mean between this point and this point. It's the same as x prime maximum. So here we have x prime maximum. And you know, n in this case equals to mg. Why? Here we have the weight, we have n is up, mg is down, equals to O because no motion along y prime. So n equals to mg. We substitute all the values here. We get minus m equals to 0.8 divided by 2, VA equals to 1.2 square plus K equals to 50 times x prime square maximum divided by 2, and here equals to mu equals to minus 0.5, n equals to mg equal to 0.8 m times g equals to 10 times x prime maximum. Okay, here we have one equation. We can calculate the value of x maximum by your calculator. Okay, we can have the answer will be you get two answers here. We have x prime maximum equals to minus 0.25 m, and also x prime maximum equals to 0.092 meter. Okay, you have one accepted value is a positive value equals to 0.092 meter. This is the answer. Okay, I think it's clear now. You have to use this relation in the case of no conservation of mechanical energy. You have to take omega f into account.